Okay, so the next presentation is also another very well-known TopCon follower, that is JTPV, Jaitai. We have Xinrui An, who is R&D Manager at Jaitai, and he's going to talk about cutting-edge cell technology to help module makers outperform the competition. So, Xinrui, the floor is yours.
Hello. Hey, good afternoon, everyone. I'm Xinrui from JTPV. It's a great honor for me to share our cutting-edge cell technologies here today, and we believe they can be very useful to help module suppliers to outperform the competition during this tough period of time. So can anyone see the slides? Yeah. So next slide, please. Sorry, next slide, please. Yeah. As a professional cell manufacturer, and our goals are to empower customers with technological innovation and to maximize power generation from improved cell structures. And in today's report, we'll highlight the technologies embedded in our latest half-cell product, Mono 2, including the advanced metallization, improved edge passivation, as well as rear optical optimization. And for those who are not familiar with JTPV yet, our standard product, Mono 1, is an N-type cell that comes in a variety of 4 wafer sizes. And it involves a range of techniques such as stacked wafer depth process, emitter metal contact optimization, super thin fingers, and super multi-bus bar. Due to time limit, I will only cover these old technologies very briefly today. Next slide, please. Yeah, the stacked wafer depth process is basically to put a pair of wafers back to back or face to face, depending on which side you want to process. And there will be slight wraparound layer on the other side, which can then be removed with single side wet chemical etch. And this technique can be applied to essentially for all the thermal processes and double our production capacity compared to standard double side processing. And we must carefully control the process parameters such as the ramp-up rate or the gas flow, because the wafers will experience thermal stress with asymmetric deposition of fumes. And the emitter metal contact optimization allows us to use less corrosive paste to reduce the amount of silver aluminum spikes for lower contact root combination. And it can lead to about 5 millivolt increase in VOC without significantly impacting contact resistance, leading to about 0.3% efficiency gain on the cell level. And the super thin fingers and super multi-bus bars are both improved metallization techniques that can facilitate thinner fingers or bus bars respectively. And we can decrease the grid spacing so that the fill factor can be greatly enhanced. For module suppliers, the use of super multi-bus bar ribbons can also reduce resistive losses and therefore increase the CTM. Next slide, please. With the development of silver paste to enable increasingly thinner fingers, cell manufacturers can now routinely print fingers under 20 microns wide. In JTPV, we have developed a novel fine line printing technique branded as the Super Thin Finger Plus to further push the limit down to 15 microns. Narrow fingers with smaller spacing can lead to reduced resistive losses in the metal grade as well as in the emitter, and also lead to less shading for the cell. This also allows for higher emitter sheet resistance to increase cell VOC, which can potentially lead to better CTM. Next slide, please. This slide shows some of our cell results. Note that we've conducted numerous experiments with different combination of screen printing masks and paste, and the one shown here is 100% relevant for mass production. With VOC and GSC roughly unchanged, the fill factor increase leads to an efficiency gain about 0.1%. This is primarily due to the improved finger aspect ratio from 55 to 70%. And in the experiment group here, we simply increase the number of fingers by about 10%. And potentially, we can also adjust emitter sheet resistance to shift towards high VOC rather than high fill factor with the same efficiency gain, which can lead to higher CTM for module suppliers. Better finger aspect ratios also makes possible a trade-off between cell efficiency and silver consumption. For instance, we may opt for lower silver usage while maintaining the same efficiency as the baseline in times of high silver price. It is easily achievable by adjusting the screen printing settings, and this strategy also leads to better cost effectiveness for our products. Next slide, please. The second feature of Mono 2 is the so-called half-cut edge passivation. Nowadays, mainstream module suppliers usually prefer half-cut cells to reduce risk losses in the module, leading to about 3% extra power output. This has been kind of standard approach since the PERC time. However, as the cell VOC increases, the influence of laser cutting on cell performance is becoming more obvious. Laser cutting may introduce silicon dangling bonds and other defects at cell edges, resulting in increased recombination of electron hole pairs. And this leads to decreased minority carrier lifetime and increases the risk for micro cracks. Generally, cell efficiency can be reduced by about 0.2%, with the most impacted parameter being the fill factor. Note that this is the case even with the so-called damage-free laser cutting, because the cut surface is devoid of any passivation layers. Next slide, please. In JTPV, we developed an edge passivation process for half-cut cells. After laser cutting, we stack the half cells together in hundreds or even thousands to deposit a thin layer of passivation film, such as aluminum oxide or silicon nitride, on the lasered edge. You can then perform an extra test and sort step to group the half cells according to their S-passivated characteristics. HEP primarily increases cell fill factor for all the cells, but there may be outliers whose JSC or VOC are also impacted somehow. So this extra test and sort step is highly recommended. From SON's VOC results on the bottom left, we find that the pseudo fill factor is increased by 0.8%, corresponding to 0.2% in efficiency. This is in good alignment with the final IV result on the bottom right. Just like the reverse process to laser cutting, the cell efficiency is almost fully recovered. In a recent experiment, which is not shown here in this page, we noticed that the thermal process itself during film deposition may improve the surface and bulk passivation as well. But the underlying physics is still under investigation. This demonstrates that there may be still room for power increase with the HEP process. Next slide, please. And this slide shows the module results. An increase of about 5 volts is found with both single glass and double glass modules. As discussed earlier, performing an extra test and sort step may further increase the power of modules made with the best beams because of more concentrated cell characteristics. And counterintuitively, cutting into halves can also slightly improve yield, as roughly 40% of the EL problems only occur in one half cell of the pair. And in this case, the cell manufacturers don't have to downgrade the good cells. And lastly, wraparound of passivation films only covers very marginal area on the cell edges and does not pose a problem for welding or aesthetics for the module suppliers. Next slide, please. Another feature of Mono 2 is the improved rear optics from the end user's point of view. Diverse application scenarios demand power generation using all possible sources, including the albedo. Therefore, it is important to reduce parasitic absorption by optimizing the properties for rear passivation layers. By modulating the layer thickness between rear fingers to form an optically inhomogeneous structure, we have improved cell characteristics and achieved the bifaciality up to 90% on the cell level. We term this technology as the wave back surface field, or WBSF. Next slide, please. And this slide shows the cell results for WBSF. An increase up to 0.15% in cell efficiency is achievable with a boost in JSC that overcompensates fill factor loss due to increased rear sheet resistance. Note that for WBSF, we have actually a wide range of parameters. For example, we can change the rear passivation schemes and also the percentage of area that receives the treatment. The higher the percentage of treatment, the larger the efficiency gain is. But in real production, we must balance the efficiency with yield and throughput, and 50% will be a sweet spot. With the use of WBSF, cell bifaciality can be increased by about 6%, as you can see from the table. Next slide, please. WBSF technology greatly broadens our application scenarios. In cases of large solar farms with adequate ground reflection or certain distributed applications like carports, the high bifaciality of Mono 2 can bring about extra power. And we also tested different background materials, including white paint, sand, concrete, grass, and water, and found up to 20% extra power can be generated from the rear for our Mono 2 cells. Next slide, please. So as the professional cell manufacturer, we have the capacity for all the common wafer sizes. And this slide summarizes our standard cell products, including 182, 210R, and 210N, with their corresponding module power. A gap of about 10 watts between Mono 1 and Mono 2 on average results from the three technologies we just covered. And noticeably, bifaciality on both cell and module levels are significantly improved with Mono 2, making them uniquely competitive for bifacial applications. Next slide, please. Compared to standard PERC, N-type modules have higher bifaciality, up to 85%, and this can lead to 1 to 1.5% extra power. And N-type modules also have better performance thanks to their lower temperature coefficient and working temperature than P-type PERC, leading to about 2% extra power. Moreover, free from light-induced degradation, N-type modules also feature lower first-year and annual degradation than PERC. This corresponds to about 1.8% power gain with an extra 5-year module lifetime. Next slide, please. So to summarize, N-type modules have the strength of being LED-free, good PID resistance, lower encapsulation loss, lower temperature coefficient, better weak light performance, and consequently higher power output than the standard P-type PERC. Next slide, please. And this slide shows the generation gains and losses caused by impacts such as temperature degradation and bifaciality, with PERC being the benchmark. We see that the Mono 2 has a superior degradation and bifacial properties than PERC and also than Mono 1, and has about 1% advantage in VOS cost and LCOE than Mono 1. And 210N modules are slightly more cost-effective than 182 modules due to their larger wafer size. And please note that this data is based on the simulation of a 10 megawatt site in Qinghai province, China, that has a dry and cold climate with good insulation. That's ideal for PV applications. For most other locations, the difference between Mono 2 and less advanced module types may be even greater. Next slide, please. Reliability indicators for N-type modules are usually well below the IEC standard of 5%, and our Mono 1, Mono 2 products show even improved behaviors, especially with the DH1000 further reduced below 3% for single glass modules. This result is very promising for the distributed market because single glass modules usually dominate that market. Next slide, please. And this slide shows the qualifications for our testing facilities from both China's CNAS and also TUV SAT. We also summarize the range of tests we can perform, including the LETID, water boil, acetic acid, pH on cell level, and the range of tests listing table for the module level, including DH, HAS, TC, etc. Next slide, please. So in summary, Mono 2 can help customers to maximize their return on investment with efficiency, reliability, as well as sustainability. It not only enhances individual module output, but also reduces the overall maintenance and BOS costs, especially in the case of bifacial applications. And in terms of reliability, taking advantage of its superb DH performance, Mono 2 is well suited for high temperature and high humidity environments with minimized degradation, and to ensure stable power output within its lifespan. And finally, using Mono 2 and also ensures you to partner with the global leader in N-type PV technology to maintain your technological advancement in the future. Next slide, please. Speaking of technological advancement, this slide shows our latest cell result certified at ISFH with efficiency exceeding 26%, And this cell exhibits extremely high VOC over 743 millivolts with excellent surface passivation. We also struck a perfect balance between JSC and fill factor with carefully tuned super thin finger plus and WBSF recipes. Note that this cell is just the 1A2 full cell, so it didn't receive any HEP treatment. And we believe if we cut it into half and treat it with HEP, it would have had even higher efficiency. And notably, all the processes here are based on industrial equipment and materials only, with very minor modifications, such as the rear side WBSF percentage mentioned earlier, demonstrating that our mono 2 cells have the potential of even higher efficiencies. Next slide, please. And finally, some background information about JTPV. We are a professional N-type solar cell manufacturer that operates 2 production bases in totaling 40 gigawatt in Zhuzhou and Huai'an, China. And we've been taking the lead in N-type solar cell shipment since Q2 last year. In the first 3 quarters of 2024, we made a total shipment of 26.4 gigawatt, among which over 90% are N-type cells. Next slide, please. Originating from China, JTPV aspires to global leadership with overseas sales teams across Europe, Middle East, and North and South America to cover all the important markets. And earlier this year, we also started the construction of 5 gigawatt cell production facilities in Oman. And we are among the first Chinese companies to set up production bases in the Middle East. Next slide, please. And this slide shows our awards on different levels, ranging from industrial, provincial, and national, as well as our partners and clients. As you can see, a lot of them are actually overseas companies. Next slide, please. And finally, here are some ESG stats. Cumulatively, JTPV has made over 80 gigawatts cell shipment and been an active player toward China's 30-60 decarbonization goals. And that's all of my presentation today. Thanks for attention.
Thanks, Xinrui. I think I got one question. So mostly you talked about what's the potential with the TOPCon. So what's in the roadmap for you when you want to move to the next level? So will you go to the back contact architecture, or will you directly step into the next generation tandem? Because you made a lot of optimization at cell level. So do you think it makes sense to go to BC, or what's the roadmap for JTI?
In JTPV, we have a very large team for the back contact cells, and we already been in the pilot stage for quite time, and we're waiting for like the both domestic and international market to for a certain time, and we can put BC in mass production. But I think we're technologically ready for BC.
Okay, so that means the next step would be the BC for you.
Yeah, but that does not only depend on technology, but also on a lot of other factors, including like the economy of the cell and also the customer acceptance, etc.
Okay, so thanks a lot for finishing on time. And if there are any more questions, please answer them in the chat window, and also enjoy our conference. I would like to move on to the next presentation.
Thank you.